So welcome back after the break. We will go on with our workshop now. In this part of the workshop, we're going to analyze our material. We will mainly focus on the pore size distribution and tortuosities, which both are very important features of our material. If you missed the first part of the workshop, or maybe you closed Geodict accidentally, let me show you how you can resume the workshop anyway. Go to your handout folder, to the folder input data, and in the folder input data you will find a NMC with CBD file. Drag and drop this into Geodict, and you have loaded the NMC with the carbon black and binder domain that we created in the first part. Also with the right color settings, if you are lucky. If you're not that lucky, go up here to the color settings, click on that, and here at ID 1 solid you can choose light gray. For the ID 2 PVDF binder you can choose green, and once you did this you can close that. And now you can go on with running the analysis on this structure. And we can go on with analyzing the material. So what we want to do is we want to have a look at the pore size distributions at first. And before I'm really doing this, let me give you some background information on what Geodict is actually doing during the calculation of the pore sizes. There are several different ways of calculating the pore sizes in Geodict. This is not only because, or it's not really a Geodict specific thing, they're just different ways of defining the pore sizes in the world. So there's one approach where you really want to know what's the body of the pore, what's the volume, so to say, of the pore. And to calculate that, Geodict fits spheres into the pores. It just looks how large may a sphere be which fits into this pore, and once it touches the border of the pore, then the sphere can't be larger anymore. So this algorithm is called granulometry, and it really gives the body of the pore, so the volumes. Then there's another very important algorithm, which is called porosymmetry. And the porosymmetry resembles something which you can also do in an experiment by mercury intrusion. And usually in the experiment, you apply a certain pressure to the sample and really press mercury into the pores, and by increasing the pressure you can the mercury intrudes into the pores, and you can back calculate from the pressure drop, you can calculate how big are my pores. But what you actually get is not really the size of the body of the pore, but of the throat. So once the mercury passed the smallest part of the pore, so here, for example, the so-called throat of the pore, it fills the entire area behind that. So assuming that the mercury intrudes from here, it has the smallest part of the pore is here, it's the throat, and then it fills the entire pore behind that throat. And so what you get with a porosymmetry is the actual size of the pore throats, and with the granulometry you get the volume of the pore, so you get the size of the body of the pore. So you can see that both definitions have their merits and are both valuable. The porosymmetry is something that you can directly compare to your experimental porosimetry results. So that is really useful to know, am I looking at the right data? Is everything okay? So just for validating. While on the other hand, the granulometry is something that you can't really access in an experiment. But still, it's very interesting to know how big is the body of my pore. So this is something unique to simulations. And we are now calculating first the granulometry in GeoDict. But the porosimetry is done really exactly the same way, and I will show you how this is done too, but we will focus on the granulometry and start with that right now. So let's do that. We go to the Analyze section, go to Porodict. This is the module you will need for the calculation of the pore sizes. And here you have the pore size distribution granulometry. If you open this drop-down menu, you can see that the second entry is pore size distribution porosimetry. And then there are also other ways of defining pore sizes. For example, identify pores, which uses a watershed algorithm. Then you can also calculate open and closed porosity and some other special things. But as I said, we are going to focus on the granulometry, and we click on Edit. One very important thing for the visualization later on is to check this box, right? Pore size distribution as GSD file. If you do this, you can later on look at your pore size distribution in 3D in colors, and that's what we are going to do. Everything else we can leave as it is. Close the dialog by clicking OK and click Run. And now, as always in GeoDict, when it's calculating, this window opens and you can see a progress bar, and you can see that GeoDict is at the moment calculating granulometry, and below that there are the sub-steps that show what GeoDict is currently doing. So when GeoDict is finished, you get again a result file popping up, similar as when we imported the image. Here's a report. We can see what are the characteristic diameters. So the D50 value, for example, gives us the diameter of a pore where half of the pores are bigger and half of the pores are smaller than this diameter. So this is a diameter of 5.1 micrometer. Then we get a table of all the pore size pore sizes for in a certain range. And if you don't like looking at this table, but are more like a visual type of a person, you can click on plots, and then you see the pore size distribution as a plot, which is much more appealing, I think. So this is the result for the granulometry, and we now know that most of our pores have a body diameter between 2 and let's say 8 to 9, maybe 10 micrometer. If you want to have a look at this in 3D now, just go to the pore size visualization tab up here in the result file. And then you see here is the GSD file where we checked the box before, and you can load this. If you click on that, you get a pop-up window again, and you can just say OK. So GeoDict loads the 3D distribution of the pore sizes into its main view window. And if you go to the main view window, you can see that there's still the structure visible in gray. And then we have the pore sizes in colors in the pore space, of course. So if we only want to look at the pore space now, because we don't have any pores in the solid material, of course, we can uncheck the structure tab up here, and you see that there's only the result field being left. Where there was the solid material before, we have now a pore size of 0, which makes sense. So if you hover with your mouse over this structure, you can see the diameter in the very bottom of the tooltip, and you can see that it's something to the -6. So you can always see the number of the pores here. Okay. And if we go to the volume field tab here, we can uncheck even the solid material so that it's that the result field, so the pore size in this case, is not visualized in the region where there is only solid material. If we do that, and also for the binder and count black domain, we are left with this kind of field. And we can play around a little bit with the clipping, because it's very nice. If you're only interested in larger diameters, you can clip into the structure, and you can see that the smaller values are disappearing now, and we are left with the bigger pores only. It's very nice. Even if you check the solid material again and do this clipping, you can see that they that the values inside of the solid material, which is 0, are vanishing directly. Okay, and now we can save this, for example, as an image, because it's looking nice. And before we do that, maybe we can also use a different renderer, or just choose another position of the structure. So like that. And then go here and say save image as, and then the image will be saved in our project folder. Again, we already did this for the import, so I'm doing this a little bit more quickly now. Save as transparent background and say OK. And then here we have already the picture from the import, and we call this granulometry to be able to distinguish from the porosymmetry, which we are running right now in a second. So this was the granulometry, and now I told you that there is another algorithm called the porosymmetry, and for comparison we are going to run this too. So if you go to porosymmetry and edit, we have again this pop-up window here opening. We can again write the pore size distribution as a GSD file, although we're not really going to look at it later on, but maybe you want to do this on your own later on. So if you check this, you still have it available. So then you say OK and run, and then we wait again for some seconds. Then we get again the GDR file, which looks very similar to the one of the granulometry. And we can go to plots again, and you can see the pore size distribution, or the size distribution of the pore throats, you could better say. And if you want to compare this now to the granulometry to see that there's really a difference, we can directly do this in GeoDict, and very conveniently. Just up here you see that this is the result file we are currently looking at, and this here is the result file, pore sizes, of the granulometry. And if you hit Shift or hold Shift and then click on the other result file, you get both result files next to each other. And we can enlarge the window a little bit, that helps. Then we go in both result files, we go to results and go to the plots. And then you can see, okay, they don't look that much alike, so they have really a difference. The shape is different, the size is different. So for the granulometry, we have smaller, in general, larger diameters than for the porosimetry, which makes sense because it's the pore body, which is usually bigger than the pore throat. But still, it's hard to see exactly, really compare exactly those two files. What you can do in GeoDict is very neat. You can go here to combine results, and then this window opens. You can choose a new GDR file, so new result file name. I would suggest something like pore size comparison and GDR as an ending. Then you say OK. And then we get a third GDR file you can see here, which is called pore size comparison.gdr. Go to plots, and then you see both plots plotted into one figure. And you can see the red one is the result of the granulometry, so here, while the blue one is the result of the porosimetry. So you can see that there are substantial differences. And of course, the granulometry leads to, in some, to larger diameters than the porosimetry. So this is very helpful if you want to compare two different results, or maybe two different methods, like in this case. You can also do this for two different structures, for example. So if you run porosimetry for one structure and for another structure, maybe NMC 622 and NMC 333, then you can directly compare the results in GeoDict in the same manner than we just did here. Just for the sake of completeness, we can also run a different algorithm that would be the identify pores algorithm. We won't do that now, but just as a hint, you can do this on your own later on. And then the pores will be identified using a watershed algorithm. So there are no spheres being fitted, but just the area is filled by GeoDict until it hits the next pore. So this again gives a different distribution of the pore sizes, and it's really interesting to compare those just to see how different the definitions are and to which different results they lead. So now let's analyze the tortuosity of our structure. But first, what is a tortuosity? I mean, most of you will probably know that it's generally defined and explained by the simple definition of the path length the particles have to take to go through the structure, divided by the distance between the 2 points in the structure. So this is not the only way of defining a tortuosity or the only possibility. There are actually a lot of possibilities of defining tortuosities and defining how to calculate tortuosity. This is a slide I have taken from a user meeting talk given by Lorenz Holzer from the ZHAW, that's the Zurich Institute of Applied Sciences. And he gave this talk last year at our user meeting. So I just took this slide just to show you how many different definitions of tortuosities are possible. There are the direct possibilities, which you can see on the bottom. For example, by calculating certain paths in the structure, for example, the percolation paths, and dividing those by the thickness of the structure, which is exactly what we have seen with only one path on the slide before. And then there are the indirect approaches, like, for example, calculating diffusivities or the diffusivity through the structure, and back calculating from this value to the tortuosity. And you can also mix both of these approaches and get different definitions. If you want to know more about this, you can have a look at the user meeting talk from last year. And if you need some information about this, just contact me, or you can directly contact Lorenz Holzer from the ZAHAW in Zurich. He will probably be very glad to help you out with your questions. It's a very interesting talk, so he really gives a broad overview of what is possible in the tortuosities, and we even included several of these definitions and their calculations in GeoDict in an app. And if you want to calculate a lot of different types of tortuosities, just contact me and I can give you the information about this app. But now we are only going to calculate the tortuosity defined by the diffusivity using the diffudict module in GeoDict. And to do that, we still have to close the GDR file from before, or we can minimize that. It doesn't really matter. Then we want to visualize the structure again so that we see what we are doing. Maybe we don't want to see the volume field at the moment. And then we go to analyze. Oh, sorry, to predict here. Predict, use the diffudict module. That's the first one. 1 second. Then choose here the bulk diffusion. These different regimes are for different types of diffusion inside of your material. It depends on the free path lengths that the particles have inside of your material. So for calculating the tortuosities, we only need the first one here, here, the bulk diffusion. And then we click on Edit. And in the Boundary Conditions tab, we choose the X and the Z direction for computational directions, so the diffusivity in X and in Z direction is being calculated. In the Solver tab, we choose a different solver, so we choose the Lear solver. And what we also do is we uncheck, if it's already unchecked, it's fine. So uncheck discard PDE solver files, and we want to write the diffusion flux into the solution file. So this is also necessary for the visualization. And if you discard these files, you cannot visualize the results either. So just keep that and then say OK and run. And then sometimes, like in my case, for example, the virus so the virus scanner is trying to check if there's something bad happening. Just ignore it, and usually GeoDict follows on the normal path after that. So here you can see again the progress bar and what GeoDict is doing at the moment. It's calculating diffusivities, which is not really surprising when we are calculating a diffusivity. Here below you usually get a plot showing the convergence of the solver. You can see how many iterations we've already done, and then the diffusivity value that we have at the moment. So, and you can see how far away the last dots are. And don't rely on the number that the time says here. It's just at 1 hour, which is not true. Just leave it running, and then you can see that the x direction already ran through. So now we still have the z direction to calculate. And if you are interested in details, you can unfold here the console, and you can see what the output of the solver is. It just does, for example, the time steps, which is calculating at the moment, and some details. So it's almost there. Here it is, and the GDR file, so the result file, pops up again. I'll minimize this. And here in the table below, you can see the results for the tortuosity. On the left-hand side, we have the tortuosity factor in x direction, which is 1.8 or 1.9 roughly. And in z direction, it's the same, more or less. So you can see that there's not much difference between the x and z direction. So the material seems to be fairly isotropical, which is nice for a battery at least. Yeah, so far to the tortuosity. And what we're going to do now is having a look at the diffusivity. And we already calculated this. And we want to have a look at the diffusivity in x direction, just because if you have a look at geodict here, you can see that x direction is the long direction while z is the short one. And z is an interesting direction for charging the battery later on, and for all the things that take place here, and tortuosities would be interesting in that direction, and even the diffusivity, because this is just the through direction for the entire thickness of the cathode. But just for visualization purposes, we choose the x direction now because we have longer path and a longer way for the particles to pass through the structure. So just for visualization purposes, we choose x direction and say load. And then we can choose which fields we want to load: the concentration, diffusion flux in x direction, y direction, z direction, or the entire diffusion flux as a vector field. Just leave them all checked. It doesn't really hurt in this case. And we say, okay, we don't need to keep the existing volume fields, which is only the process distribution. We are finished with that one. So can just overrun this, or we can delete the process distribution. So now you can see we still have the structure being shown. And we have a result field in the pores visible. And here you can see this is the diffusion flux we are looking at. We're not really interested in what the structure, what we're going to do now is beautifully visualize the diffusion flux through the structure. So what we do is we go to the volume field tab. If it's not already chosen here, choose diffusion flux. Then we go to the Streamlines tab and check it. Then we uncheck the volume field tab. And you can see that there are still some things inside of the structure, but it's hard to see what it is. So we go back to the structure tab, and we can clip into the structure now from each side. And you can see what is left is the streamlines, so the path where the particles go through in a diffusion process. And to make this look beautiful now, I would suggest to check the invert checkbox here so that everything that we clip is being shown and everything that we don't clip is not being shown in the structure. So leave this in X direction with 0, in Y direction 0, 2, and in Z direction we choose 106, also be 100. And for the upper values we choose 500 for X, we choose 290 for the Y direction, and we leave it with 200, so the maximum possible value in Z direction. So you can see here we have the streamlines going through the structure, and we still can see the structure, so that gives some orientation for the eye. We can also go back to the Streamlines tab and choose Streamlabs and let it play, so then we can see where the particles are actually moving. If you can't see this very well, we can choose a thicker line for the streamlines. So, as we're going to leave this as an image, we're going to back to Streamlines. Make it a little bit thinner again because that's just too much now. Maybe 2 or 2.5. And choose an angle that you like. So maybe something like that. And we again go to File and save this as an image. Say OK. We call this, for example, diffusion flux. And then save this. So we have saved this as an image too. And with that, I will leave you again for the break. And you can ask questions right now, or as I said, you can get a coffee or something. I will be available in the chat, and my colleagues too. So if you have questions, please ask. If not, see you in 10 minutes.